I'd like to start off with a quick introduction. Name is Nathan Leemkuil. I have been chatting with Ibrahim for, I don't know, a little over a year and a half. I think we met in a networking conversation and just kind of grew from there. I work for a company out of the DC metro area, Washington, DC metro area, as the VP of operations. And that company is Connected DMV. And if I describe what we do in very short order, we are a combination of a economic development association and a consultancy. We work to bring about opportunity for emerging technologies in the DC area in particular, but expand that nationally and globally. Two of our primary initiatives include quantum, and the other initiative that we are just starting up is space consumerization, or commercialization, I should say. How do we grow that frontier and develop and bring new technologies out, establish new policy that is going to be beneficial across the board and to help govern that. I'm not a scientist, I'm not a researcher, not even a quantum engineer. I'm a business guy that gets up in the morning, and the idea that I can positively impact the global community through the promotion, advancement, and enablement of emerging technologies and trends, that's what drives my desire to get up every morning and to go about and do business, and that's what I enjoy doing. Sorry about that. I started my career not with Connected DMV. I started my career with Accenture Consulting, 13 years working for energy, critical infrastructure, developing their financial HR, did some cybersecurity on the side there, moved to a small startup in cybersecurity and developed a cybersecurity product for industrial IoT, and then moved to an operations role with Connected DMV. My friend had contacted me about that. So today's topic, why quantum and why now? And I think part of what I want to communicate in this is quantum computing is not sci-fi anymore. It's out there. It is progressing. Are there issues? Absolutely. Are we at the point of quantum computing taking over the world? No. But we are and we are moving forward, and it is becoming a business imperative, right? And I guess the question that then comes, why quantum, why now? What if there are some problems that are fundamentally too hard or too complex for today's computers? Is there an alternative? And if so, what is that alternative? And I think that alternative sits in the realm of quantum. So what is quantum? Quantum computing is a new type of computer. It uses the rules of quantum physics to tackle the problems that today's classical computers struggle with, right? And so classical computers are constrained by the way they process information. Instead of bits, a quantum computer uses qubits. Instead of having two states for any one of those bits at any independent time, 0 or 1, a qubit can be measured as how close it is to behaving like 0 or how close it is to behaving like 1, or what mix of both at the very same time is that state in. And that property is known as superposition, right? So it's degrees of 0, degrees of 1, and how close, or how do I describe, how do I articulate the state of that? And so one of the things I've got to think about with quantum computing is these qubits are in constant flux. It only matters when they are measured, right? And so that is one of the challenges that we have with quantum upcoming. Another property of quantum computing that exponentially enhances the power of the qubit is what we call as entanglement. And we think about this as the qubits are tightly linked. The state of one qubit directly impacts and affects the state of every other qubit in the system, right? Classical computing, every bit is independent. It is 0 or 1, and it is read as 0, 1 independently of all the other bits. It doesn't change based off of the other bits. With quantum computing, every bit is, or every qubit is dependent on every other qubit. And so you have this ever fluctuating environment. And due to entanglement, the unending possibilities of what could state be, right? And this is what really is the core method to solve that. It works by amplifying probability of amplitudes. And one way to think about this, and where the research behind quantum computing is going, is to think about a pond, right? Glassy water, no, and you throw a pebble in. And where these ripples are coming together, they're going to either amplify and make a larger ripple, or they're going to de-amplify and cancel each other out. And where you have a tendency, or the theory behind quantum computing is where you have a tendency of amplification, that is an indicator that your quantum computing algorithms that you're processing is moving in the direction that you want to go. Where it is de-amplified, then you are moving away from your desired end state. All right. Lots of other, again, I'm not physicist to explain all that. I'm trying to explain at a very high level. And so as we look at interference, what we're looking at is measurement of the state of the bit, the qubit at any given point is only matters at the point of measurement. Well, with interference, the amplitude of the waves of interactions is indicated and for by and Grover's algorithms, right? So I don't know what I was doing. I apologize. We think not a and that is where we need to take that technology. So what are some common misconceptions? And by addressing misconceptions, how does it clarify the realm of quantum, right? One of the misconceptions is that with quantum computing, we try all the answers at once, right? We're just throwing quantum processing power at all answers at once. And that's not the case, right? What we are doing and where the advantage of or quantum computing comes, the appropriate or the right path and avoid the brute forcing, minimizing the brute forcing of evaluating every possibility and make sure that we're going down the right path at the right time and being more efficient at that. All right. What's another misconception about quantum computing? Quantum computing will replace classical computers. No, right? Quantum computers are going to be good at those highly complex scenarios that we mentioned. We'll get into those a little bit more. And they will leave the current tasks that classical computers are very good at alone. It's a different model. They aren't meant to work together. And what we will have is this unique mix of quantum computing and classical computing that is joined. And the concept is going to be, is this a problem? Is this a use case for quantum computing, or am I better gained following the classical model, right? Another misconception: quantum computers are faster at everything. No, same thing, right? They won't replace classical computers. They'll have speed ups, but it's particular problems. Factoring, some searches, some simulations, not everything, right? Another misconception: each qubit stores exponentially more than a data than a bit, right? Not exactly. A system of qubits has exponentially more possible amplitudes, which is what gives quantum computing its power, but it's only at the point of measurement, right? So every qubit is measured at a given point in time. And when that qubit is measured, that we get any true real data out. That's the readout point, right? So it's not that we have this massive qubit that can store exponentially more data. It's that we have a qubit that has exponentially or massively more amplitude in what it. All right, entanglement lets you send information faster than light. No. Entanglement, this idea that every qubit is together, creates strong correlations, but in and of itself doesn't transmit usable information. It's very volatile, in fact, right? Quantum computings can already break all encryption today. We're getting better at it. We're finding additional ways to improve our fault tolerance, and it does threaten public key schemes, but we're not there yet. Now, is that one of the biggest threats to our computing systems? And one of the major issues that we see coming up is that quantum computings will have the ability to break RSA encryption. Have they done it? Yes. But is it readily available, and will it be a tomorrow's issue? I don't know. I don't know when it's going to happen, but I think it will. And but it's not there yet. All right. One more misconception: we're just a couple of years from practical quantum advantage in everything. I think that is really the crux of the discussion of what we run into when we start talking quantum computing. It's, when is this going to happen? Well, there's rapid progress. There's multiple real world use cases that are still experimental. We're building large and error corrected systems, and we're getting better at it, but it's not sweeping the market yet. In the next 3 to 5 years, potentially. When it happens, I think it's going to be a cascading effect of when we realize the power of it, when we have access to these systems on a readily available basis, that we're going to see major changes very, very quickly around quantum and use of issues. They're powerful, but they're limited. Our error correction and stability may remain major challenges. We are still working on that, right? And what is it that I have to remember about quantum computing? It's a different model of computation. It's not magic, and it's not classical computing. It is in a different field. It is in a different perspective. We have to use them together, and we have to really analyze, where does the advantage of quantum come, and how do we use that to solve specific problems? That ties into point number 2, right? Useful for specific problems. It's not a universal speed up. It's not going to be used for everything. It's not going to be, I have a quantum computer sitting on my desk versus my classical computer sitting on my desk. Why? Because the work that I do is traditionally not that complex, right? I need speed. I need something that is efficient. I need something that is able to complete those tasks quickly, but I don't need a quantum computer. All right. Where is then quantum being used today? We do have computers out there. IonQ, IBM, Google, Amazon. The list goes on. There are some countries where we don't know what their quantum state is. It is highly, highly secretive, and they don't share it with us, and we share it with them, right? But we know that they're out there and they're advancing in that realm. But what are they doing with it? Right? If we look at the use cases, and one example of connected DMV as just one thing to do is global industry challenge with Quantum World Congress. And what the global industry challenge is, it's a competition, a hackathon for quantum computing algorithms. And they present that out. This are inaugural GIC, Global Industry Challenge. They had over 700 participants, 48 different countries across the globe that presented solutions to multiple different challenges from research. Had one challenge around asphalt binding, so the development of material. We had another challenge around the finance and risk management, predicting weather patterns, and using quantum algorithms to help optimize what insurance companies are going to do and how. And the question is, but there is a I don't know specifically. Another thing that we now have to think about quantum is there are really three areas of quantum research. Obviously, quantum computing, right? Process simulation, optimization, and cryptography, crypto break mountain ranges work using these very small sensing or accurate sensing devices in my navigation, in my imaging, in my geophysics. So there's three other pillars of quantum that are being pursued. Why now? What is it that's happening in the market that is putting us on the precipice, the precipice of moving forward in that quantum solution, where I think we're right at the verge of it's going to be something here in the next 3 to 5 years. Quantum is absolutely advancing on all fronts: hardware innovations, real world demonstrations. More and more smaller companies are getting into it, and they're creating accurate working quantum computing. Are hard scaling, right? IBM, Google, Amazon, they're all racing for that next biggest ship. And some that Riken announced a 256-bit superconducting quantum computer, and they're targeting a quantum machine by 2026. Well, we're a year away from that. This was in April 2025. This is that quantum advantage really there, and how do we prove that? Is the fault tolerance really there, and how do we prove that? Right? Another major thing that's happening on the is the software engineering. The algorithms tools are being tested classical simulators. We have the ability to do a global industry challenge and bring college students and industry experts in their spare time a quantum computer to develop their ideas, develop their technologies. Another major player, governments are globally recommending action, right? US, Canada, India, Germany, United Kingdom, they're all pursuing and setting goals of enhancing their quantum ecosystem, understanding the need for it, understanding the desire for it, understanding requirement for where they will move to a quantum environment. One of the biggest indicators that I would say is the current state of our economic stakes, right? This graph on the was a 1-year summation on the 4 biggest players, or what we saw as the 4 biggest Quantum World Congress in 2024. So it's from September 2024 to September 2025. IonQ's net value went up by almost $12 billion. That's ridiculous. D-Wave up. You can see the numbers, right? There is so much investment, so much investment of these systems. Our governments, and it's all going in that direction. Right? Quantum is happening. But what are the challenges? It continues to grow, but the scaling up the number of still a challenge that's out. When will we hit that pinnacle? When will we hit that breaking point? I don't know. Is my guess. Right. The other major challenge is I don't think we've exhausted cases for quantum computing. It is so new, it is still developing. We don't know where that is going to go. All right, so what's our call to action? And this is kind of where my company, Connected DMV, steps in. Across the globe, the primary action is advancing a global quantum ecosystem. This has to be a coordinated investment, a collaborative effort to bridge that. We have to be working together and sharing information and guiding and directing. That's one of the things that we do at Quantum World Congress. Annual convening, that show up over 3 days. And from our international forum to our national updates, it is all about collaboration. What's going on? How are we working together? What do we need to do next? Where are the theories and the ideas going? How are we building agriculture and logistics? Optimizing supply chain, crop yields, predictive modeling, food securities, etc. On the health front, on the finance and industry front. I think those are all different areas where we could enhance and continue to work together on this issue. Now, I don't have a closeout. I'm good with that. But what I will do is open it up to a discussion on this was an introduction, right? I don't have all the answers. I never intended to have all the answers. It's where I think the environment is going, where the technology is going. What are your guys' thoughts?